Hi and welcome to my channel. Today I want to talk about Faraday's law of induction, but I want to explain it without resorting to flux and loops, but just try to give a simpler explanation. It is based on the Lorentz force, and as you'll see, you can understand induction with the Lorentz force. A reminder, what's the convention for magnetic fields perpendicular to the plane? If the magnetic field lines are going along this arrow, the tip of the arrow is marked as a point in the back of the arrow is marked as an X. If you see a diagram with the field as a dot, it means the field is pointing towards you. And if you see an X, it means the field is pointing away from you, just like the tip and the back of an arrow. The field line density represents the strength of the field, so the arrow representation gives you both the intensity and the direction of the magnetic field everywhere in space. Here's an example of a region with a magnetic field that's pointing away from you, and here's an example of a magnetic field that's pointing towards you. Let's recall what the Lorentz force is. When you have a charge that's moving in 90 degrees angle relative to a magnetic field B, there is a force which is proportional to the velocity of the particle, the charge of the particle, and the strength of the magnetic field, which is the density of the field lines. The direction of the force is given by the famous right-hand rule. When your index finger is pointing towards the direction of the velocity and your middle finger points towards the magnetic field, the Lorentz force will be in the direction of your thumb. In the general case, when the velocity direction is not 90 degrees to the magnetic field, the force would be given by the vector product of the velocity and the magnetic field. If you actually want to calculate it, it's just the charge times the absolute value of the velocity times the value of the field times the sine of the angle between the velocity and the magnetic field. The Lorentz force can be thought as another electrical field. When the charge is moving inside a region with a magnetic field, it sees an extra electrical field. It senses an additional electrical field. Instead of viewing the Lorentz force as just a force, you can view it as an effective electrical field whose magnitude is the vector product of the velocity and the magnetic field. So the charge doesn't know if it's subject to an electrical field with an effective value E, effective, or it's moving in a magnetic field. Even if there's no charge and you're in some frame which is moving relative to the magnetic field, you will sense an electrical field. Of course, you will need to have a charge to measure this field, but the field is very real for an observer moving inside a magnetic field. The reason for this electrical field is related to Einstein's theory of relativity. It just says that if you move in a region with a magnetic field, it appears to you as a combination of an electric and magnetic field. But don't worry, I'm not going to talk more about relativity. So this is just the frame where you're not moving relative to the magnetic field, you see just the magnetic field. And when you're moving relative to the magnetic field, you see an extra electrical field shown in green. So what's the electromotive force? When you're moving inside a magnetic field, you sense a perpendicular electrical field at the direction of the Lorentz force. The total sum of the field over the length of this rod is the potential difference, which is defined as the electrical field times the length of the rod. If you place a conducting rock in a magnetic field, you will be able to measure this voltage. The actual voltage will be the scalar product of the length of the rod and the electrical field if the electrical field is parallel to the rod. It's just a product, but if there is some angle, you need to take that into consideration and multiply by the cosine of the angle between the rod and the direction of the electrical field, which is the scalar product. So let's start by solving some classical problems. First of all, let's look at a rod which is moving on a wire frame. The frame is not moving relative to the magnetic field. The rod is the only moving object here. So when the rod moves, it sees an electrical field shown here by the green lines. Charges start building up. They're pushed by the electrical field. Positive charges are pushed upwards and the negative charges are pushed down. You start having a current in the circuit, and suppose the resistivity of the circuit is R, we know that the potential difference, or the electromotive force, is the field times the length of the rod, which is the velocity times the field times the magnetic field times the length of the rod. The current is just the voltage over the resistance, and we can find the current. Now again, the only thing that's moving relative to the magnetic field is the rod, which is in blue, and all the rest is not moving. So it doesn't sense any electrical field. Okay, second problem, which is also a classic. We have a wire frame which is moving, the entire frame is moving into a region with a constant magnetic field. So here all the frame will be sensing the electrical field, but only parts shown in 1 and 2 are affected by this field because they are parallel to the electrical field, the Lorentz electrical field, so they feel it. When the wireframe starts entering the field, you have rod 1 sensing the electrical field and you have a voltage on it, of course. Rod number 2 is out of the field, so there's no voltage and you start having a current. The other parts of the frame are not affected by the field because they are not parallel to the electrical field, but of course they conduct current. When all the frame is inside the field, you have a voltage across rod 1 and rod 2, and the voltages are in the same direction because they feel the same field. And of course the two voltages are the same, so they cancel each other and you have no current in the circuit. The third problem is a bit more complicated, but it can be easily solved using the Lorentz force technique. Suppose you have a wire frame and it's rotating inside a region with a magnetic field. Again, as you remember, the rotating rod sees an effective electrical field. What's the direction of the field? It is perpendicular to the magnetic field and to the velocity, so the electrical field is radial, because the velocity is going around the circle. So first of all, what's the electrical field induced in the rod? And second question is what's the magnitude of the total electromotive force on the rod? So the field as seen by the rod is different as you go along the rod because the rod is moving at a different linear velocity at different places along the rod. The angular velocity is constant, but the linear velocity, which is what we need to calculate the electrical field. We need to divide this rod to many segments, and each segment is moving at a different linear velocity. The linear velocity is given by omega, which is the angular velocity times the radius from the center. The electrical field, which is just the velocity times the magnetic field, is given by V times B. The electromotive force is the sum of all the electrical fields along the rod. Because the field is changing, we have to do a little integral, and the result of this integral is square dependence on R. When you substitute the outer boundary, you get a half times E times omega R squared. Sorry, half times B omega R squared. Let's discuss a little bit about work and energy. Suppose you're moving the rod, the current is flowing through the rod, and charges, of course, are moving. The charges that are moving due to the movement of the rod are also feeling the Lorentz field, which is perpendicular to their motion. So you actually have to do some work to move this rod. The power you need to exert on the rod in order to keep it moving at a constant velocity is given by the force times the velocity. The force you need to apply has to cancel all the other forces in order to be moving at a constant velocity. The force is B times the current times the length, which is the electromotive force times the current. Of course, this is the electrical power that's dissipated in the circuit. So to summarize, when a charge is moving in a magnetic field, this is an electrical field. This electrical field is giving rise to the electromotive force or the voltage. And in my next video, I will discuss the case of changing magnetic field, which we did not discuss here, and we see how to deal with that case.